Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over molarity and equation stoichiometry. So basically what I'm going to be showing you is how you can use molarity as a conversion factor to convert to moles. So up to this point I've been harping on this idea of whenever you're doing stoichiometry, your goal is to take whatever unit they give you and get to moles as soon as you can. So convert that to moles, because as soon as you can get it to moles, you can use the mole ratio in your balance equation to convert from one thing to another. So that strategy still applies when you're dealing with molarity. So it's just that with molarity, you now have a new way of getting to moles. Right. So in the previous videos, I've written this down. I'll write it down really quick here. So you're going to go from where do I want to do this? So they give you a unit, some unit of mass for substance 1, and then you're going to convert that to grams. Substance, oh, here, let's write this. So, sorry. So we're going to have grams substance 1, and then you're going to convert that to moles, right? Moles, and that's going to be of substance 1. And then you're going to convert that to moles of substance 2. So substance 2. And then from there you're going to go to grams of substance 2. And then from grams to some other unit if they're asking for another unit. So unit of mass, some unit of mass for substance 2. Okay? And then I was saying how, okay, so from here to here, you need a conversion factor. Some conversion factor to convert from the unit that they give you of mass to grams. And then to go from grams to moles, you're going to use the molar mass of substance 1. I'll put substance. So substance 1, excuse my writing. And then from here to here, from moles to moles, you're going to use the mole ratio. I'm just going to write mole ratio to convert. And then here, substance, so moles of substance 2 to grams. Again, you're going to use the molar mass of substance 2. And then here again, some conversion factor. Right, some conversion factor that they want you to use or that you can use to convert. Let me write this better here. So molar mass of substance 1. Okay, so now here we can use molarity. Remember, molarity is moles of your solute per liter of your solution. So if they give you a volume, right, then you can use that molar, and if they give you the volume of a substance, and they give you the molarity. You can use the molarity as a conversion factor to convert the volume to moles, and then you're right here, right? So the other thing you could do here, so let's say we're given, instead of moles, they give us, let's say over here, they give us a volume. So instead of units of mass, they give us units of volume, right? So maybe it's not liters, maybe it's milliliters. So then you'll have to convert that to liters, right? Liters of your solution. So they give you milliliters of solution, right? Or maybe they give you yeah, we won't. Yeah. So let's just say milliliters. So they give you milliliters. You got to convert that to liters, and then you can convert from liters to moles using molarity, and I'll write that here. So mol. So I'll write that here. Molarity, capital M. Right? So now we can go from units of volume to liters and then convert liters to moles using molarity. Here, again, it will be some sort of conversion factor. Right? And then now you're on the main highway. So once you get to here, you can go this way, you can go this way, right? It does, wherever you need to go, you can go. You can get off the highway again. So here, the important thing is that now that you're here at moles, you can use the mole ratio to convert from one substance to the other. Once you're here, you can go wherever you need to go in the problem. You can go to grams if you want to. You can go to grams if you want to. You can go to some other unit of mass if you need to, or you can go to a different volume, another volume of a different substance. So substance 2. So again, you could then from here convert, right? You can convert to liters. Again, using the molarity of a different substance. So again, we're using molarity, right? So there we're using molarity. Again, that's going to be M as in molarity. So I'll do capital M there. So I can use molarity again to convert moles to liters of my solution. And then from there, I can go to milliliters if they want milliliters. So now we're kind of using a different conversion factor in order to convert and do the stoichiometry that we need to do. Okay, so now that I've got that out of the way, let's go ahead and work on this problem. And I'll show you how we're doing this. So how many milliliters of 2.00 molar NaOH are necessary to neutralize 25 milliliters, 25.00 milliliters of a 1.50 molar phosphoric acid? So they're giving me the volume and molarity of phosphoric acid, and I want to know how many milliliters is needed to neutralize all of that acid. I have 2.00 molar NaOH, which is a base. So I'm going to use a certain amount of volume of base to neutralize the acid. So how can I do this? Well, the first thing I need is a balanced equation. I need an acid-base neutralization equation. So that's what we need to start with. So basically what you need to do is you need to treat your acid and base and do kind of a double displacement reaction. If you don't know what I'm talking about, or you're unfamiliar with writing the neutralization reactions of acids and bases, then go to my videos on that. I have a few videos on writing your balanced equations for acid-base neutralization. I'll show it here too as well. So first thing you need to do is write down the reactants. So one reactant is NaOH. That's going to be aqueous plus, and this is phosphoric acid is our other reactant. Phosphoric acid is H3PO4, and that's aqueous. And then whenever you do your acid-base neutralization, just like with your ionic reactions, your double displacement reactions, we're going to treat these like ions, even though acids are not ions, but they do ionize. So we're going to take the inside, or we're going to take the outside ions, put them together, and the inside ions, put them together. So here we have sodium going with phosphate. So sodium has a +1 charge. The phosphate ion has a -3 charge. We need 3 sodiums to balance the charge. So here we're going to have Na3 PO4 for the first one. And then the second one, we're going to put our hydrogen together with the OH. That's going to make water. So we have H2O, and that's a liquid. And then we're going to have to figure out the state of matter of sodium phosphate. And that's going to be aqueous as well. Okay, so there's our equation. Now we have to balance it. So here I have metal first. I'm going to do metal. So sodium, I have 1 there. I have 3 there. So I have to put a 3 here for the sodium. So that's balanced. I have 1 hydroxide here. The hydroxide here reacts with the 3 hydrogens. So I have 3 hydroxides, 3 hydrogens. That's going to come together to form 3 waters. So I should have a 3 here. And then I have my phosphate here. So I have 1 phosphate here. I have 1 phosphate. So that's balanced. So everything's balanced here. So now that I have my balanced equation, I can do my stoichiometry. So the other thing that I want to really emphasize here is the way there's maybe 2, maybe 3 ways of solving this equation, or solving this problem, I should say. But the way that I show is the way that how should I say this? The conversion factor way. So I'm gonna solve this by using the molarities they give me as conversion factors. So anytime they give you a measurement that relates 2 units together, like this over this or this per this, use it as a conversion factor. So in this case, molarity is moles per liter. So I'm going to use that as conversion factor. So here I have to recognize that anytime they give me molarity, that's a conversion factor that I can use. So I have a molarity here of my phosphoric acid, and I have a molarity here of the sodium hydroxide. So the only other information they gave me is the volume. So that's what I'm going to start with. I'm going to start with the volume of the phosphoric acid they give me. I'm going to convert that to volume of the sodium hydroxide. So let's go ahead and get this started. So I have 25.00 milliliters of the phosphoric acid. So that's H3PO4, okay, over 1. In order to use the molarity as a conversion factor, I need to convert this to liters. This is milliliters of solution. I want liters of solution. So I'm going to have to convert this to liters. So I'm going to need a conversion factor. So here I am at the volume that they give me, which is milliliters. I got to convert that to liters. So I'm going to use the 10 to the third milliliters, or 1,000 milliliters of my H3PO4. solution is equal to 1 liter of the H3PO4 solution. So milliliters cancel out. Now that I have liters, now I can use molarity as a conversion factor. So the molarity of the phosphoric acid is 1.5 liters of solution, 1.5 moles of the solute, which is the H3PO4, per liter of the solution. So I'm going to multiply that by my next conversion factor. So here I have liters of the solution on top. So that tells me I'm going to put it on liters on the bottom. So I have 1 liter of the H3PO4 solution. And then on top, I'm going to have moles. How many moles? 1.50 moles. So 1.50, excuse me. Sorry about that. So I have 1.50 moles of the H3PO4 that is in the solution. So liters of the solution cancel out, and now I have moles of the H3PO4. Now I can use the mole ratio between the phosphoric acid and the sodium hydroxide, which is here, 3 to 1. So now I can use that mole ratio. Okay, so I'm going to put here, since I have moles of H3PO4 here, I'm going to put 1 mole of H3PO4 on the bottom. So 1 mole H3PO4, and then on the top it's going to be 3 moles of sodium hydroxide. And so here the moles of the phosphoric acid cancel out. Now I have moles of NaOH. Now here I am. So I've gone from milliliters to liters to moles, and now I'm at moles. I have moles of one substance, that's my phosphoric acid. And now I use the mole ratio to get to here. What are they asking me for? They want how many milliliters of the NaOH. That means that once I'm here, I'm not going to go this way. I'm going to go this way. So I'm going to have to convert the liters of my NaOH solution and then to milliliters, some other units. So let me write that down. So here it's going to be some unit of volume. And you're going to use some conversion factor. Again, some conversion factor here. So I'm going to continue down here. So we're going to multiply. So I'll continue down here. So we're going to multiply by the other conversion factor. So moles. I want to go from moles to liters. So I need a volume, and that's where the molarity of my NaOH comes in now. So that's 2.00 moles per liter. So I have moles on the top here. I'm going to put moles on the bottom. So 2.00 moles of NaOH, and then that means 1 liter of the NaOH solution is on top. So moles of NaOH cancel out. Now I have liters of NaOH on the top. And now finally they want milliliters. So I'm going to convert liters to milliliters. I'm going to use this relationship again, but now I'm going to flip it. So I have liters on the top. So I want 1 liter of the NaOH on the top, on the bottom, and on the top I'm going to have 1,000 or 10 to the third milliliters of NaOH on the top. So liters of the NaOH cancel out. Now I have milliliters, and so now I am done with the setup. So now all I have to do is multiply across the top, divide by everything on the bottom, and I get my answer. And when I do that, I get, what did I get? I get 56.3 milliliters. 56.3 milliliters of NaOH. So this is the volume of NaOH that's required to neutralize completely 25 milliliters of this 1.50 molar solution. So 56.3 milliliters of this 2 molar NaOH solution is required to neutralize 25 milliliters of this molar solution of phosphoric acid. Now, for those of you who are interested in the significant figures, you might be wondering why I have 3 sig figs here for my answer, and that goes back to the sig figs here. So remember, the rule when you're multiplying and dividing is that the number of sig figs in your answer should be the same as the measurement with the least number of sig figs. You always ignore the exact relationships. So any metric to metric, so liters to milliliters, that's going to be exact. Again, it's got to be in the same category. So this is metric volume to metric volume. Same thing here. We have metric volume to metric volume. So these we ignore. Mole ratios we're going to ignore. 1 to 3 is an exact relationship. So the only thing we need to look at is the molarities and the volumes that we were given. So here we're given 25.00. That's 4 sig figs. Here we have 1.50. That's 3 sig figs for the molarity. And then here we were given 2.00. So that's 3 sig figs as well. So 3 is the smallest number. So therefore, we have 3 digits in our answer. So that, ladies and gentlemen, is how you solve an equation stoichiometry problem with molarity. So I hope this was helpful. If you enjoyed this video, then please, by all means, like the video, share the video, hit that like button over there somewhere, and also make sure that you subscribe to my channel. Yeah, that's what I want to say. Subscribe to my channel. And when you do, make sure you click on the notification bell and click all, so that way you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question that you want me to answer, or a problem you want me to go over for you to help you with, or if you have a topic you want me to cover, I would love to do that for you. Thanks for joining me, and have a great day.